In this video, we'll look at measurement tools and how they affect the circuit being measured. In lab, we used a multimeter that could measure voltage in a circuit, it could measure current in a circuit, or it could measure resistance in a circuit. We had to use different jacks. There was always the same jack where we put our black probe, that's the common. There was a different probe for voltage or resistance where we'd put our red probe, a different jack. And then there could be two different probes for current, one for low currents on the order of 200 to microamps to 200 milliamps, and another jack for high currents. We'll also look at why we must use different jacks for that, the internal resistance of the meter itself. So the tools we used were an ammeter that measures current or the movement of charge. The symbol in the circuit we could use is a circle with an A internally to show that we in fact had a meter in that circuit and we've changed the circuit. The voltmeter measures the voltage, the potential difference across two different sections of the circuit, and an ohmmeter measures the equivalent resistance between two different sections of the circuit. So since the ammeter is measuring current, the current must flow through it. Since the same current flows through elements that are in series in a circuit, the ammeter must be placed in a position that is in series with where the current is that you want to measure. So if we have, for example, a circuit with an EMF device and two resistors wired in series, then the same current flows through all elements in this circuit. If we want to measure the current in this circuit, we're going to have to break the circuit somewhere and insert the ammeter. So if we broke the circuit here, we could then perhaps insert an ammeter between the EMF device and this first resistor. So if that's what we do and that's where we insert our ammeter, this is in fact the current that we will measure. However, we obviously have changed the circuit in order to do that. To not affect the equivalent resistance within this circuit, then the equivalent resistance of this ammeter must be zero. Or essentially, this ammeter must behave like a short circuit. We said a short circuit, the definition of that is there's no voltage drop across it. And in our circuit diagrams, all these wires represent ideal conductors that have no resistivity, so they have no resistance to the movement of charge. Of course, that's relative to the resistances that exist in our circuit originally. There's no ideal zero resistance, except for some genuinely great work that we're doing with superconductors in the physics community. So an ideal ammeter has zero resistance to the movement of charge through it, just like an ideal battery or an ideal conductor. A real battery has internal resistance to the movement of charge, and we represent that internal resistance as a resistor so that the potential difference across the real battery from A to B will be less than, so our VBA will be less than this EMF device whenever there's current flowing, because there'll be some potential voltage drop across its internal resistance. The current delivered to the load that's connected to this ideal battery can be found using the loop rule, or it can be found using Ohm's law. We have an EMF device with these two resistors in series, so it's this EMF divided by the load resistance and the internal resistance of our battery. As long as that load resistance is much greater than the internal resistance of the battery, then the current will still equal approximately our EMF divided by the load resistance. So we can actually use a lemon to drive a circuit, but a lemon has a very high resistance to the movement of charge, on the order of about 1,000 ohms. This really could be quite large. A potato also can be used as a EMF device, but it also has a very high resistance to the movement of charge, so it can't deliver much power. A quality battery can have a very low internal resistance on the order of 0.01 ohms. That's much smaller than the resistances in circuits that we've looked at so far. So if we look at the ammeter now, if we want to insert the ammeter into this circuit to measure the current, we put the ammeter in series, And that ammeter represents additionally an internal resistance, just like our ideal EMF does. So we can represent that as a little resistor. We'll call that resistance our subscript A for ammeter. And now we can see that our current in the circuit, instead of being RL, or our EMF divided by RL plus the internal resistance of the battery, we have to include in that plus our RA. So we're going to decrease the current through the circuit by inserting an ammeter. So let's look at some examples. Let's let our load resistance be 5,000 ohms and the internal resistance of our ammeter about 5 ohms, which is a pretty good internal resistance of an ammeter. And then an internal resistance of the battery, we'll let it be a good battery. It only has about 0.01 ohms of internal resistance. So without the ammeter in the circuit, we should expect our current to be the EMF divided by 5,000 plus 0.01, and that 0.01 will be insignificant relative to the 5,000. It's a factor of 10 to the fifth less than our load resistance. But our I prime, we'll call it, when we measure it and we insert our ammeter. Now instead of measuring the current in the circuit without the ammeter, we're measuring it with the ammeter, and we see the current with the ammeter. If we take the difference, or excuse me, the ratio of the two, 0.9990. So we have less than 1%, about 0.1% effect on the circuit itself. If we however, we decrease the load resistance to 500 ohms, and we look at the same analysis, we see now we're on the order of 1% difference that our measured current will be relative to, measured current with the ammeter in the circuit relative to what it would be without the ammeter in the circuit. If we continue further and we decrease our load resistance to 50 ohms, so it's only 10 times greater than our ammeter resistance. Now we're on the order of a 10% error in what we're measuring in our circuit with this 5 ohm resistance ammeter. So that's why it becomes important if we're trying to measure smaller currents, then we need to have a smaller internal resistance in our ammeter. So now let's take a peek at the voltmeter. The voltmeter measures potential difference, so that means it measures the difference across 2 points in a circuit, the difference between those two positions. So we can use voltage division if we just have two resistors in series sharing the same current. And we know that the voltage across this load will be our EMF times that load resistance divided by the sum of all the resistances in the circuit. The current, of course, will be EMF divided by RS plus RL. Then we multiply that current by RL to get that load voltage, and that's how we come up with our voltage division. So that's how we're measuring it. So we've got to put our voltmeter in. So we put our voltmeter in and we put it across and we connect it to these two positions in the circuit. And we've in fact put our voltmeter in parallel then with our load resistor. So to not affect the equivalent resistance of the circuit, the voltmeter's resistance has to be very high. So if we remember our equivalent resistance in parallel, Req is equal to then 1 over RL plus, that's RL plus R, 1 over RV, the equivalent resistance of the voltmeter. So we want this to be very large, so this is approximately 0, so that could be approximately equal to 1 over RL, or equal to RL. So we want that to have very large, or ideally infinite resistance. Infinite resistance, then it's going to look like an open circuit. Open circuit, no current flows through it. We want this current I that's flowing through the circuit, it's flowing here, we want it to continue to flow through our load resistor so that 0 current flows through our voltmeter. Of course, if 0 current is flowing through our voltmeter, then we're not going to be able to measure the potential difference across it. So we're always going to get some current to flow through that voltmeter, and that's what the meter needs to measure, but it affects the circuit. So our ideal, or without the meter, without the voltmeter in the circuit, we have our VL. With the voltmeter in the circuit, we have our RL prime, or our new RL with the RV across it, where it's the product divided by the sum. So the parallel resistance is always less than the resistance of the load resistor. That resistance being less than that, our voltage will also be affected by that, and we get our load voltage being RL divided by RS plus our RL prime. So in review, an ammeter measures current through a wire, so it has to be placed in series with the circuit you want to measure. We want that internal resistance to be very small, or ideally zero. Our voltmeter in turn measures voltage across a circuit, so its internal resistance is in parallel with the circuit. We want that internal resistance to be very large to minimally affect the circuit that it's measuring. So let's look at an example of something similar that you'll do for homework. If we have a circuit, again, with just two resistors, R and R naught, we'll define them here, connected to an EMF device, and we want to use this circuit to measure what is the resistance of this resistor. Now this is similar to what we did in lab, through your Ohm's Law lab. So we could put a voltmeter across the resistor, and an ammeter in series with the resistor. In this scenario, we're putting the voltmeter across the resistor and the ammeter. So this ammeter is going to measure the current in this direction. Our voltmeter is going to be measuring this voltage, and that'll be our V prime and our I prime. So what our circuit has, it will have our R is going to be equal to V over I, but once we measure it, what we're measuring is an R prime, which is our V prime over I prime, and this is what we're going to state to be our measured resistance. So we need to represent the internal resistance of the ammeter and the internal resistance of the voltmeter in our circuit. So here we've separated them from the ammeter itself and shown the 3 ohms of the ammeter in series with the ammeter, the 300 ohms of the voltmeter in series with the voltmeter. And now we want to compare. In this case, we should get that our R, which is equal to V over I, is equal to 85 ohms. Here we have to do a little different analysis, because now we have 300 ohms, not even in parallel with the 85 ohms, but in parallel with the 85 ohms and the 3 ohm resistor. So we've affected the circuit doubly by putting 2 measurement tools in the circuit at one time. And how we chose to measure the voltage across the resistor, we're measuring it also across the ammeter. We could have set this up so we measured with the other side of our voltmeter here instead of here, and that would give us a different voltage. So how we measure our circuit does affect what measurement we're going to get. So this is for you to do as a homework problem, but again, just what we're trying to find is your IS prime and your V prime in our new circuit. One approach could be to take this entire set of resistances and find the equivalent resistance of the 300 ohms in parallel with the 85 plus 3 or 88 ohms, determine the total current. That current then we see is going to divide, so not all the current being delivered by our EMF device is delivered to our resistor, which is what we intend. Some of it needs to be delivered to our voltmeter, and of course the resistor has the ammeter in series with it, so it changes the power needing to be delivered by the EMF device as well. And this 300 ohms is quite low for a voltmeter, at least a digital voltmeter like we use. However, it's not so unusual if it was an analog meter. So try this for homework, and we'll see you with the next video.